Welcome to the Explainer. It feels like artificial intelligence just appeared. One day it was something out of science fiction, and the next it's writing our emails, creating unbelievable images, and powering tools we use every single day. But here's the thing. This overnight revolution was anything but. It was a slow, deliberate climb. Think of it like a grand staircase of incredible ideas built one step at a time over the last decade by researchers all over the world. Each step rests on the one before it, leading us to this incredible moment.
So that brings us to the big question, right? How did AI get so powerful so quickly? It wasn't magic. The answer is actually hidden in plain sight, tucked away inside a handful of absolutely groundbreaking scientific papers. And today, that's what we're going to do. We're going to put on our detective hats and follow the trail of these key ideas piece by piece to really understand how this amazing technology was actually built from the ground up.
All right, so our journey has to start at the most fundamental challenge of all. Before an AI can do anything, it has to be able to make sense of the world. So how do you teach a machine to represent something incredibly complex, like a photo, a song, or a sentence, using nothing but cold, hard numbers? This is the quest for representation.
This right here is the absolute bedrock concept coming from a pivotal paper back in 2012. Now, to get what a huge deal this was, you have to understand how things worked before. Early AI was all about handcrafting features. It was like if you wanted an AI to identify a cat, you, a human, had to sit down and painstakingly program a checklist for it. You tell it, okay, look for pointy ears and whiskers and a furry tail and these specific eye shapes. It was brittle, it was tedious, and it didn't scale. Representation learning flipped the entire script. It basically said, forget the checklist. What if we build a system that can figure out what a cat looks like all on its own? We just show it thousands or millions of pictures of cats, and it automatically discovers the features that matter. It learns the catness of a cat by itself.
Okay, so once the machine is learning on its own, the next question is, how does it store what it's learned? Early models used something called a local representation. The best analogy is a giant switchboard with a million light switches. Every single concept in the world, every word, every object, gets its own dedicated switch. Cat is one switch, dog is another, run is a third. It's simple, but you can see the problem, right? It's impossibly inefficient. If you learn a new word, you have to add a whole new switch to the board. And the switches for king and queen are just as far apart as king and aardvark. There's no relationship. The massive breakthrough was distributed representations. Now, instead of a single switch, an idea is represented by a unique pattern of lights across, say, 300 switches. The idea of king isn't one switch, but a specific combination of on, off, and dimmed lights. And this is where the magic happens, because now related concepts have similar patterns. The pattern for king is actually very similar to the pattern for queen. In fact, you can do a kind of conceptual math. If you take the pattern for king, subtract the pattern for man, and add the pattern for woman, the resulting pattern is incredibly close to the one for queen. It's not just storing data, it's storing relationships.
The other huge idea that makes all of this work is something called the manifold hypothesis. Now, that sounds super technical, but the core idea is actually beautiful and intuitive. Imagine the space of all possible images. Think of a 1000 by 1000 pixel image. Each pixel can be any color. The number of possible combinations is astronomically huge. It's a high-dimensional space of near infinite static and noise. But, and this is the key, images of actual real-world things like human faces only occupy a tiny, tiny structured fraction of that enormous space. The hypothesis says that this meaningful data doesn't just splash around randomly. It lies on a kind of smooth, winding, hidden surface, a manifold, that twists through that vast wilderness of noise. So the AI's job isn't to explore the entire infinite wilderness, it's just to learn the map of that one specific winding road where all the good data lives. This assumption radically simplifies the learning problem.
Okay, so now we have the core principles. The AI knows how to learn representations, and it knows to look for them on these hidden manifolds. We've got the map, but now we need an engine, a really, really powerful engine that can navigate that map, especially for something as complex and layered as human language. And this brings us to the next giant leap forward.
So around 2014, if you were working on machine translation or language understanding, you were hitting a wall, a hard wall. The standard architecture at the time, called an encoder-decoder, had a fundamental flaw. It would read an entire sentence, in, say, English, and it was forced to compress the entire meaning of that sentence, all its nuance, its grammar, its intent, into a single, fixed-size mathematical object called a vector. It was like being forced to summarize the entire War and Peace novel into a single 280-character tweet. It doesn't matter if the sentence was "I love you" or a complex legal clause a paragraph long, it had to be squished into that same-sized box. And as you can imagine, all the details, all the context just got lost in the compression. This was the bottleneck, and it put a very low ceiling on how well an AI could ever understand language.
The solution, proposed in a 2014 paper, was just revolutionary. It was so intuitive. The researchers asked, what if, instead of forcing the model to remember everything at once, we just let it look back at the original text whenever it needs to? Think about how a human translator works. They don't read a whole paragraph, memorize it perfectly, and then write the translation. No, they read a bit, write a bit, and constantly glance back and forth, focusing on the most relevant part of the source text for the specific word they're translating right now. This paper gave the AI that ability. As it generated a translation, it could pay attention to different parts of the input sentence. The simple, powerful idea of attention didn't just ease the bottleneck, it completely smashed it.
This one idea, attention, turned out to be so powerful that a few years later in 2017, a group of researchers published a paper with one of the boldest titles in AI history, "Attention is all you need." They basically threw out the old, complex architectures and built an entirely new one, the transformer, using nothing but this attention mechanism. The way it works is kind of like a souped-up database lookup. At every step, the model formulates a query, which is like asking, what information is most relevant right now? It then compares that query to a set of keys, which are like labels for all the other pieces of information in the sentence. Based on which key is the best match, it then pulls the corresponding value, the actual information itself. And it does this millions of times, with multiple attention heads looking for different kinds of relationships all at once. It builds up an incredibly rich, layered understanding of context.
So, with the transformer, we had our new super engine, and the race was on. For the next few years, the mantra in the AI community was simple. Bigger is better. Build bigger engines. But the next truly critical breakthrough wasn't about building a bigger engine. It was about figuring out the right kind of fuel and just how much of it to use.
So for years, all the big labs were locked in this arms race to build larger and larger models. The thinking was more parameters equals more intelligence. It was a brute force approach. Then in 2022, a paper from DeepMind, famously known as the chinchilla paper, just dropped a bombshell on the whole field. They ran hundreds of carefully controlled experiments and found a fatal flaw in the bigger is better logic. It turned out these massive models weren't just big, they were starving. They were being massively undertrained. The researchers discovered a set of scaling laws that showed the secret to optimal performance wasn't just having a bigger model, but scaling the amount of training data you fed it perfectly in lockstep with its size.
And the proof was just undeniable. You can see it right here. Chinchilla, their new model, had only 70 billion parameters. It was dwarfed by giants like their own Gopher model, which had 280 billion. Yet Chinchilla absolutely crushed Gopher on a wide range of benchmark tests. How? It's simple. It was trained on 4 times more data. This was a David and Goliath story. The smaller, better-fed model beat the lumbering giant. This discovery completely changed the economics of AI. It wasn't just about who could afford to build the biggest engine anymore. It was about who had the best fuel recipe.
Okay, so the models had now pretty much mastered text. They were incredibly powerful. But we don't experience the world through text alone, do we? Our world is a rich tapestry of sights, sounds, and language all woven together. So the next great frontier was teaching AI to connect these different senses to see and hear the world in more than one modality.
The first attempts at this were logical, but maybe a little bit clunky. You basically had 2 main strategies. There was early fusion, where you take your raw image data and your raw text data and kind of mush them together right at the beginning of the process. Then there was late fusion, where you'd have one model process the image, another process the text, and then you'd combine their final decisions at the very end.
The cooking analogy works well here. Early fusion is like mixing all your raw ingredients into a single batter before you bake. Late fusion is like cooking two separate dishes and then just plating them together. They both work, kinda. But you get the sense a much more elegant and powerful solution was out there.
And that elegant solution arrived in 2021 with OpenAI's CLIP model. It used a completely different and, frankly, much cleverer approach called contrastive learning. Instead of the hard task of teaching an AI to look at a photo and generate a perfect caption from scratch, they gave it a much simpler job. Imagine you give the model a batch of 100 photos and their 100 captions, but you shuffle them all up. The model's only job is to figure out which photo goes with which caption. It has to find the 100 correct pairs, and just as importantly, learn that the 9,900 other possible pairings are all incorrect. It's learning by comparison. By doing this simple matching game millions and millions of times, it starts to build a deep, intuitive, shared understanding of the connection between visual concepts and the words we use to describe them.
This matchmaking idea wasn't just clever, it was incredibly efficient. In some key tests, like zero-shot learning on the famous ImageNet dataset, this contrastive approach was a whopping 4 times more data efficient than the older predictive models. But the real game changer was what it enabled, a truly flexible, general-purpose vision model. You could now point CLIP at a task it had never been explicitly trained for, and it could often do it, just by using its shared understanding of images and language. It was a massive step towards a more general AI.
So let's take stock. Our models are now multi-talented geniuses. They can read, they can reason, they can see, but that genius came at a very real cost. These models were now colossally huge, with hundreds of billions of parameters. This made them incredibly expensive to train and, crucially, almost impossible for anyone outside of a few giant tech labs to adapt or fine-tune for new tasks. A new challenge emerged. How do we tame these giants we've created?
And then, in 2021, another incredibly clever engineering trick called LoRA, or low-rank adaptation, came along and totally changed the game. The core insight was just brilliant. Instead of trying to retrain the entire massive 175 billion parameter model every time you want to teach it a new skill, which is just impossibly expensive, you freeze it. You don't touch a single one of those pre-trained weights. Then, you inject these tiny, new, trainable adapter modules into the architecture. It's exactly like having a massive, fine-tuned engine in a race car. You don't rebuild the whole engine for every different track. No, you just tweak the suspension, change the wings, adjust the fuel mix. LoRA is like those tiny adjustments. You're only training the tiny new chips, not the giant engine they're plugged into.
I mean, just look at these numbers. They're staggering. For a giant model like GPT-3, full fine-tuning means wrestling with all 175 billion parameters. With LoRA, you're only training about 17 or 18 million. That's a reduction in the number of trainable parts by a factor of 10,000. It's absurd. The amount of expensive GPU memory you need is slashed by 2/3. And the best part? You get all this with basically no drop in performance quality. Overnight, this technique democratized AI. Suddenly, fine-tuning these colossal models wasn't just for a few elite labs. It became possible for researchers, for startups, even for dedicated individuals in the open source community. It was a huge deal.
So with all these incredible pieces now on the board, we have a way to represent the world, a powerful engine to process it, an efficient fuel recipe to power it, multiple senses to perceive with, and a way to tame it. The final question becomes, what do we build? The focus is now shifting away from building specialized tools for single tasks towards a much grander ambition, a unifying theory of intelligence. One of the most powerful ideas emerging in this area is the geometric deep learning blueprint. The theory here is that all of these different AI models we built, convolutional neural networks for images which operate on grids, graph neural networks for social networks, and even transformers for sequences, they aren't really that different from each other. The hypothesis is that they're all just expressions of the same fundamental principles of geometry and symmetry, just applied to different kinds of data structures. It's a search for a kind of unified field theory of AI, a common language that could let us build models for any task on any kind of data. And this grand ambition leads us directly to the current frontier, so-called any-to-any models. We're moving beyond models that just take text in and put text out. These new systems are being built to understand and generate content that seamlessly weaves together text and code and pictures and audio, all within a single coherent output.
Think less like a chatbot and more like a creative partner that can help you build a modern web page or a presentation from scratch. This is so much closer to how we humans actually think and communicate, in a rich, multimodal stream.
So there you have it. In just 1 decade, we climbed this incredible staircase of ideas. We went from teaching a machine how to represent a simple idea to building a universal engine to understand all of human language, to finding the right fuel to make it truly powerful, to opening up its senses to the world, and finally, to taming it. Each step was essential. And now that we're here, standing at this new plateau, it leaves us with one last, fascinating, and maybe even unsettling question. As these models get better and better at reflecting our world back to us, are they just a mirror? Or are they starting to paint their own pictures and build a new world entirely?